In this video, we're going to be talking about orbital hybridization, which is a process that atoms can take to make their electron orbitals a little bit more conducive to forming different types of bonds. You will still need something to write with, you'll still need something to write on, and once you have all those ready, let's go. So the first thing we kind of have to keep in mind when we're talking about orbitals is that orbitals are wave functions, right? And wave functions or wave equations can be combined. When you combine wave functions, you form what are called hybrid orbitals. Now, all of the orbitals in a particular set of hybrids have the same amount of energy. They're what's called being degenerate. So just like we said, all p orbitals in this 2p sublevel are degenerate because they have the same energy, this will also be the case whenever you form a hybrid orbital between s and p or individual orbitals. And the reason why atoms will do this is because it makes bonding significantly easier, right? When you form a chemical bond, what's actually happening is that the electron clouds for those two orbitals overlap with each other. And to make that overlap easier to achieve, it helps if the orbitals have similar shapes and similar energies, right? So that's what hybridization is doing. It's creating shapes and energies that are about the same that will allow these atoms' orbitals to overlap with each other effectively and form a covalent bond. Now, we're going to go over three different types of hybrid orbitals, different combinations of s and p orbitals hybridizing. We'll go through what it looks like before the hybridization, what it looks like after the hybridization, and I also have images of what each of these three hybrids looks like in three-dimensional space. So we'll start off with what's the most basic type of hybrid orbital. The single most common one is what we call an sp3 hybrid. If I draw out the electron configuration, right, so we'll take the 2s sublevel and the 2p sublevel, draw out all of those orbitals. What's going to happen is that when we combine all four of those orbitals together, you get four hybrid orbitals that are called sp3. Right? It's called sp3 because we took one s orbital and three p orbitals. So when we do this, they all have the same energy. And because they have the same energy, it makes bonding to other sp3 hybrid orbitals or other hybrid orbitals in general a lot easier. Now here's a diagram of what an sp3 hybrid will look like. And you notice that it looks kind of almost a little pyramidal. We'll get into the actual names of the shapes in a later video. Right, but those large bulbs that you see are the hybrid orbitals that are involved in bonding, and they are evenly spread out around the atom in three dimensions. Our second type of hybrid orbital is we're only going to take two p orbitals and combine them with the s to make a hybrid. So because we add together the s and two of the p orbitals, we get three hybrids here. These hybrids are what we call sp2. And then we have one p orbital that's still not hybridized. It's still its normal ordinary p orbital. Okay, so we get that. This is what it looks like to the right. It forms a flat geometry, 120 degrees between all the different bonding orbitals. And then that p orbital will actually do something we'll get into in a couple of minutes. All right, so this is an sp2 hybrid. We also have what's called an sp hybrid. So the s orbital and one of the p orbitals will combine with each other, and they'll form two hybrid orbitals that are both sp. So notice, the number of orbitals we put into a hybrid are equal to the number of hybrid orbitals we get out. Okay, that's how wave equation combining works. So for an sp hybrid, two hybrid orbitals, and then we have two p orbitals that aren't hybridized that will do something that we'll get into in another moment. Okay, so why are hybrid orbitals important aside from making it a little bit easier to bond? Well, the first thing is the type of bond that you form is determined by how the different orbitals overlap. So our next slide or two, our next couple of slides, I should say, we're going to go over the two main different types of covalent bonds that you're going to form and how they form between whether or not the orbital is or is not a hybrid. The other reason why is because you saw in those diagrams how all those shapes had angles on them. The shape and angle of the bonds is determined by the type of hybrid orbital you use to make it. Okay, so anything that's sp3 hybridized has a bond angle of 109.5 degrees and will always take on some variation of that equilateral pyramid shape that we'll get into in a later video. Okay, so that's why these are kind of important. So we'll get into the two types of bonds. The first bond is what we call a sigma bond. Right, so a sigma bond is what happens when two orbitals overlap head to head. Right, so direct overlap of two orbitals. Whenever you form a bond between any two atoms, the first bond that you always form between those atoms is a sigma bond, no matter what. Okay, so carbon and hydrogen, each carbon-hydrogen bond is a sigma bond. If you form a double bond, the first bond you form in that double bond is always a sigma bond. Okay, so that's always the first one. One of the questions I'm going to ask you is I'm going to say, here is an atom, here's a molecule, or here's a bond. Count up the total number of sigma bonds and other types of bonds that you have. So first bond, always sigma. The other key thing about this is rotation is always allowed around a sigma bond. So that CH4 molecule right there, I can freely rotate that molecule around any of the carbon-hydrogen bonds. Rotation is completely allowed. Now, our other type of bond's a little bit more structured, shall we say, and that is what's called a pi bond. So sigma bond, you have direct overlap, the two orbitals merge into each other. Pi bonds are when you have side-to-side overlap of orbitals. That can only happen between p orbitals themselves. So unhybridized p orbitals are what are responsible for forming these pi bonds. So as we can see in the diagram on the right, you have that p orbital pointing up and down, because remember, p's are shaped like dumbbells. If they get close enough to touch side to side, they'll overlap that way and form what we have down bottom, which is that lovely little band on the top and on the bottom. That is our pi bond. So first bond formed between any two atoms is always sigma. The second bond, the third bond are always going to be pi bonds. Okay, so a single bond is just a sigma. A double bond is a sigma and a pi. A triple bond is a sigma and two pi bonds. And again, as far as rotation, because the pi bond is kind of combined where it is, there's no rotation around that bond. When you form a double bond, the molecule cannot rotate around that. Okay, that will become kind of important later on when we start talking about isomers and electronic structure and that sort of thing. Okay, so this is orbital hybridization. The individual atomic orbitals, so our s orbitals and our 3p orbitals, will combine in different combinations to form hybrids that make it possible to form single bonds, double bonds, and triple bonds between atoms. Okay, so that is it for this video. We'll see you in the next video where we're starting to talk about drawing molecules.